Hello, welcome to Maths with Martin. I'm Martin, an A-level teacher for over 7 years, and in this video we are going to look at parametric equations. The reason why I want to pick on parametric equations, if you're doing the Edexcel exam board, there were no parametric equations on paper 1, so it's almost guaranteed to come up on paper 2. In this video, we're going to just do a little overview of parametric equations first, a little crash course in them, and then I've got 3 exam questions that I've taken from the international A-level papers, so they're still very similar to what you will see in the Edexcel papers in the UK, but just maybe questions that you haven't seen before. So let's get started. So what are parametric equations? Well, we can define the coordinates of a point x, y, not in terms of each other, but as functions of a third variable, which we call our parameter. This parameter could be t or theta, the most common ones that we'll come across. We can think about it like describing the location of a moving object. So instead of explaining the vertical position based on the horizontal position, so y in terms of x, you could describe the horizontal and vertical positions at any moment in time, which is our t. You'll often be asked to convert parametric equations into Cartesian equations. Cartesian equations is what we're just using when we've got x's and y's. So you've seen Cartesian equations all this time. You probably never thought to call them that previously, but Cartesian equations is just what we're talking about when we have x's and y's. And sometimes you'll be asked to go into Cartesian form. So when you start off your parametric equations, the goal will be to eliminate that t or eliminate that theta. So you just then have it in terms of y and x. Sometimes you'll just do that by rearranging. Sometimes you might use trig identity. So you might use something like sine squared plus cos squared equals 1, or sine 2 theta equals 2 cos theta sine theta. We'll see an example where we use a trig identity later with that. It's often useful when we're changing from parametric to Cartesian form to remember these 2 bullet points that you can see in the top right. So the domain of f of x is the range of x when it's defined parametrically. And it'll often be easier to find the range of x in its parametric form than to get your domain for your Cartesian curve. And if you find the range of y when you've defined it parametrically, you can then find the range of your Cartesian equation. Yeah, again, we'll see some examples of that in a bit. At the bottom here, we've got a bit of calculus as well, because you will be asked to differentiate and integrate. And I think on paper 2 coming up, I would imagine there's going to be either some differentiation or integration of parametric, potentially both. So to differentiate parametric functions, it's nearly almost going to always be easiest to do this rather than find the Cartesian equation for the curve and then differentiate that. Okay, it can be done sometimes, but often it's the harder or the longer way to go about it. So to differentiate parametric equations, what we want to do is to differentiate y with respect to t and differentiate x with respect to t. Normally that will be pretty simple differentiation to do that you'll get in the exam. And then if you do dy by dt divided by dx by dt, well, those dt's cancel, and then that gives you dy by dx. So as I said, that will often always be easier to do it that way than to find the Cartesian, which sometimes that's really hard to do anyway, and then differentiate that. And what you might have to differentiate might be quite complicated as well. So often we want to go with that approach there that's on the bottom left. And then finally, you may get asked to integrate parametric equations. So what we can do is do a little trick that normally if we're integrating, we've got our function y in terms of x, and we're integrating with respect to x. So we just have the integral of y and integrate that with respect to x. But what we could do is we could multiply by dt over dt, which is basically like multiplying by 1. And in terms of our parametric, we'd then end up, we could then write this as y times dx by dt, and then you'd be integrating with respect to t. So what you do here is you just plug in y as a function of t, and then you multiply that by dx by dt, and then you're integrating, that will now all be in terms of t, and then you just integrate that with respect to t. And yet again, it's often going to be much easier to do that than to get the Cartesian form and then try and integrate that. So let's put all of this into practice and see some exam questions. Okay, so we're going to look at the first of 3 questions that we're going to look at here. And if you want to follow along with these questions, have a go yourself first. If you do look in the description below, you'll find the link to all 3. I'd really recommend that you have a go at these questions first. So we've got our figure here with the part of a curve with parametric equations x and y that are defined, as you can see there on your screen. And we're told that the curve cuts the x-axis at the origin and at the points A and B. And the first part of this question, we need to find what the coordinates of A are and show that the coordinates of B are 20, 0. So let's think about our strategy here. Now, a common thing that we need to use all throughout A-level maths is that when I have a curve that is cutting the x-axis, that should make me think, okay, curves cut the x-axis when y equals 0. So we've got y equals t cubed minus 4t. So if I want to find out where this is cutting the x-axis, well, I can set my y to 0 here. Okay, graphs cross the x-axis when y is 0. So we set y to 0, and then I'm going to start to solve this. So I'm going to start by factorising out the t. Okay, you've got a common factor of t there. Just be really careful with that you don't just divide through by t, because you will be losing one of your solutions when you do that. So we're going to just factor out the t, and then I've got t squared minus 4, and to solve that I could just use the difference of 2 squares there. So t squared minus 4, that's going to be t plus 2 and t minus 2 when I factorise that. So I've got 3 solutions, t equals 0, t equals minus 2 and t equals 2. It's to be expected that there were going to be 3 solutions because there's 3 places where it crosses the x-axis. So what we're going to do now, so basically at A, the origin, and B, they all have some value of t here, okay? Now we have to be careful, we can't just assume that A, O and B are just going to be, for our t coordinates, they're just going to go in order, okay? We're going to need to test each of these t values to see what the corresponding value of x will be. So firstly, we'll see what happens when t is 0. So when t is 0, we plug that into our equation for x. So when t is 0, we just get x as 0. So now at the origin there, you've got for x is 0, y is 0, the t value that they share, this is the kind of key thing with parametric equations. Think about it, the x and the y at each point are going to share a value of t. They're sharing that value of t equals 0. Okay, so we didn't need to find that one, but that's just confirming that the t equals 0 gives us the origin there. Okay, so we're going to test this second value of t. So we're going to look at what happens when t equals minus 2. So we plug it into our equation for x. So we do 2 times minus 2 squared minus 6 times minus 2. And when I evaluate that, I end up getting 20. So this is a positive value of x. So this must represent b here. So now at this point b, the t value is going to be minus 2. Okay, so when t equals 2, this means x is 20, so b must be 20, 0, okay? This is what I was asked to show. So I've done that bit. So hopefully this other value of t should give me the coordinates for a. So when t equals 2, I'm going to substitute that into x equals 2t squared minus 6t. And when I do that, I end up getting x as minus 4. So the coordinates of a are going to be minus 4, 0. So at this point a here, the t value is going to be 2. So as I said, look, it doesn't actually go, going from left to right, the t values are not ascending necessarily. So just make sure that you do actually go and test them there. Okay, so that's part A done. Let's get into part B now. Now in this part, we're asked to find the equation of the tangent to the curve at B. So let's just do a little sketch of what that's going to look like. So we've got our tangent. So it's only a very rough sketch here, but we've got our tangent here to the curve at B. Okay, so remember that tangent line is going to have, at that point B, is going to have the gradient of the curve is going to be the same as the gradient of that line at that point B. Okay, so we need to find the equation of that line. So to find the equation of the line, I need to find the gradient and I need to know a point on that line. Okay, now I know that B has coordinates 20, 0. That's why they had that show that part for part A. But what I'm going to need to do is find the gradient. So you can pretty much think that if you see, find the equation of the tangent here, when we're talking about parametric equations, we're going to need to do some differentiation, okay? We're going to need to do some differentiation to find our gradient function. So we mentioned at the start, to find dy by dx, we could get the Cartesian equation of the curve. But that's going to be a bit tricky, and also then we might have to do some tricky differentiation afterwards. So let's find a quicker way of doing that. And rather than find the Cartesian and then differentiate that with respect to x, what I'm going to do is I'm going to do dy by dt, which is right a little bit different. I'm going to do dy by dt, and then I'm going to then divide that by dx by dt. Okay? Hopefully you look at x and y there and think, okay, differentiating them shouldn't be too much of a challenge. And then I can get what dy by dx is. So we know that if y is t cubed minus 4t, dy by dt is just going to be 3t squared minus 4. And if x is 2t squared minus 6t, dx by dt is going to be 4t minus 6. So dy by dx will be 3t squared minus 4 divided by 4t minus 6. There's no need to do any simplifying here. We'll leave it as that, because what we want to now do is find what the gradient is actually going to be. So this is our gradient function for the curve. So wherever I am on the curve, I could put in a value of t to find the gradient at that point. We want to find it at B. And as we looked at earlier, so B has the coordinates 20, 0, but they share that common parameter of t equaling minus 2. So at that point B, the value of t is going to be minus 2. So we're going to sub that in to our gradient function. So we just pop that into our gradient function here. And when I do so, I get a gradient of minus 4 over 7. Okay, so that is my gradient at that point B. So now we know that 20 is the x-coordinate, 0 is the y-coordinate at B, and the gradient is going to be minus 4 over 7. So now we can just plug it into y minus y1, so that's just going to be y, times you've got your gradient of minus 4 over 7, and then you're going to do x minus x1, so x minus 20. And then you can just times both sides by minus 7, and then multiply the bracket by the 4, and then just rearrange it to get the required form. In the final part, we're told that that tangent to the curve at B cuts the curve again at point P. So if we go back to my diagram here, you can see this line is going to cross here at P. Okay, so what we're going to do is use algebra. We're going to find the x-coordinate of P. Now, yet again, we could find the Cartesian equation of the curve and then just solve simultaneously with the equation of that line. But that's going to create more work for us. So what we're going to do is we're going to start off with what we just showed in part B. You know, there's always usually a reason why, you know, they'll get you to show that because you will most likely need to use that a bit later on. And what we're going to do is we're just going to plug in y and x from our parametric equations. So we're just going to replace y with t cubed minus 4t, and we're going to replace the x with 2t squared minus 6t. Okay, just our parametric equations from before. And don't forget that minus 80 is still there. And then what you can do is just start to expand and simplify. So I'm just going to expand the first bracket, expand the second bracket, and then I'll just collect those t's together. Okay, and so I've got to solve this equation. Now you might be tempted just to shove it all in your calculator, but this question does say find using algebra the x-coordinate of P. So we need to show some working here. So we're going to need to figure out how we could start solving this cubic. Now, we're looking at where the line and the curve are going to intersect. And I already know that they intersect at B, where the t-coordinate is minus 2. So I know that t equals minus 2 is a solution of this. So t equals minus 2 is a root of this equation, which means t plus 2 is a factor. Okay, using the factor theorem to know that when I put in minus 2, that's going to be a root. So t plus 2 must be a factor. So I can just do some division here. And this might upset some people that I'm going to do polynomial division like this. But whichever way you do it, if you do long division, that's absolutely fine. Do whatever works for you at this stage. So I'm looking to make the 7t cubed. So I know I've got 7t squared there. And I've got 14t squared there. Now 14t squared, now I need to have a plus 8t squared, so I need a minus 6t squared. And t times the minus 6t squared, to make the minus 6t squared that is, I need minus 6t. Then 2 times minus 6t is minus 12t. And then if I'm on minus 12t, I'm going to make minus 52t. So I've got minus 40t. Okay, so then this needs to be minus 40. And 2 times minus 40 makes minus 80. So that all works. So if I know t plus 2 is a factor, so I can write this cubic as 7t squared minus 6t, take away 40, and I times that by t plus 2. And then I want to factorise this, which again is not the easiest thing. Now, to be fair, this is where you probably could cheat a little bit. You know, you can put it in your calculator and you'll see that you get 2 roots here, and then you can kind of fudge it by showing the fully factorized form here. So the thing is, you can only see there's actually only 2 places where it crosses, so you do know that you're going to get a repeated root as well, and that repeated root is going to be the t plus 2. So I can just factorize that. And I'll be thinking as well, so, to make the 7t squared, I'm going to need 7t and a t. To make the 4t, there's quite a few options there, but as I said, one of these roots is going to be repeated, so it turns out it's the t plus 2. But like I said, you can kind of cheat a bit here and just put it in your calculator to see that it's going to be that. So we ignore the -2 solution, that's the one we already knew. The one we're looking for is this other one here, so I'm looking at 7t minus 20 equaling 0. So t is going to be 20 over 7. And then you can just plug that value of t back into your x equation. And we just get that x is going to be minus 40 over 49. We don't need to go and find what y is, we just were asked to find what x is. Okay, let's look at our second question. So we've got a curve C that's defined by the parametric equations, and we're going to show that the equation of C can be written in this Cartesian form of g of x equaling this fraction, and we also need to find the domain of this, which is x is greater than k, where k is some constant to be found. So what we're going to do in this question is we're going to take our parametric equations and we're going to show what the Cartesian equation is going to be. So basically we want to eliminate the t here, that is going to be our goal. So we've got x equals 1 over t plus 2, and we've got y equals 1 minus t over 3 plus t. So what I'm going to do is, because it's in the form y equals g of x, so I want this to end up being y equals some function of x. So what I'll do is I'll look at the first equation and I'm going to make t the subject. By doing that, I can then eliminate the t. So to make t the subject, I'll just have to take 2 from both sides, and then I can just multiply through by t, divide both sides by x minus 2, and we'll get the following here. What I can then do is take that t equaling 1 over x minus 2, and I can substitute that in to my equation for y over here. So we get this situation where we've got a fraction within, well, we've got fractions within a fraction. And I always say to my students that if ever you see something that you're like, ugh, that doesn't look nice, well, let's think about how we can deal with that thing that isn't that nice. Okay, so if the thing here that you're not liking is the fractions within the fraction, well, how can we get rid of those fractions? And my thoughts would be, well, if we multiply our numerator and denominator by x minus 2, then I'll be able to get rid of these fractions. So let's do exactly that. We're going to times the top of this by x minus 2. So I need to times both terms on my numerator by that. So 1 times x minus 2. And then if I multiply 1 over x minus 2 by x minus 2, it's just going to cancel down to 1. So I've just got that minus 2 that's on the outside there. And then I'm also going to multiply the denominator by x minus 2. So I'm going to do 3 times x minus 2. And when I multiply that fraction of 1 over x minus 2 by x minus 2, that's just going to leave me with the 1. So then what I can do, I can just simplify the top, which will just leave me with x minus 4. And then on my denominator, got 3 times x, 3 times minus 2 for minus 6, add the 1, and that gives me -5. But we're not quite done there yet, because I'm told that g of x equals ax plus b over cx plus d. So I found what a, b, c and d are, but I'm also told that x is greater than k. So this is the domain of the function. So basically I need to find out what the domain is of this. So what we're going to do is going to use something we talked about at the start of the video, in that the range of x as a function of t will be the domain of my Cartesian. So what I'm going to do is find the range of x equals 1 over t plus 2 for t being greater than 0. Okay, just note that at the start of the question you're given this domain. So if we can find the range of this, then that will be the domain of my Cartesian equation. So let's just do this over to the side here. If I sketch what x equals 1 over t plus 2 is, so if I was just to sketch 1 over t, it would just look something like this. But then what's going to happen is that plus 2 means I translate it all up by 2 units. Okay, I'd always recommend that you draw sketches here, because just visually it will help you see what the range is. But I also mentioned that actually we've got this domain of t being greater than 0. So actually I don't need that part either. So this is just my graph of x against t. It seems a little bit weird to have x as your vertical, but that's what we're plotting here. We're plotting x against t. So this is what the graph looks like, and we can see that this graph is just always above, the value of x is always going to be above 2. So the range of x is going to be x is greater than 2. So this is going to be the domain of g of x will be the same, okay? It will be x is greater than 2. So just to kind of clarify everything there and just make it all nice and clear what my answer is at the end, g of x is x minus 4 over 3x minus 5, and x is greater than 2. So that 2 is that value of k. And then finally, we're asked to state the range of g. So there'll be a couple of different ways we can go about it. Because it says hence or otherwise, I can use what I've just found out in that part A to do this. So I could do it with the Cartesian. Alternatively, I could just find the range of y when it's defined parametrically, because that will be the range of g of x. But because it says hence, I'll go with looking at what I've just shown there. So what we just had, just to write it on here again, so we just had that g of x was x minus 4 over 3x minus 5, and we know that x is greater than 2. So if I want to find the range of this, I need to think about, well, what can I put into this? Okay, well, my domain is x is greater than 2. So the smallest value of x I can put in is going to be, well, just above 2. So let's look at what happens when x is 2. Okay, so when x equals 2, okay, it can't actually equal 2, but we can then kind of adjust our inequality from there. So when x equals 2, g of 2, so we plug that in, we end up getting, so we do 2 minus 4 over 3 times minus 2 minus 5. When we do that, we get minus 2. And then what I want to look at is, okay, well, that's the lower limit of this, being 2. Now, you could, if you wanted, it's only 2 marks, so I wouldn't go into this in that much depth, but you could show that this is a one-to-one function. Basically, as x gets bigger, g of x is actually going to get, g of x is going to tend to some limit here as well. But what I'm just going to do is look at what happens when x tends to its upper limit, which is infinity. Okay, if x is greater than 2, the smallest value you can put in is 2. I mean, technically not 2, but just above 2. And the largest value you can put in is going to be, going to infinity. So what happens is that when x tends to infinity here, when you plug this in to g of x, well, as x gets really, 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 really big, the -4 and the -5, they don't matter anymore. So you're just doing, this basically just tends to x divided by 3 over x. So the x's will cancel. So g of x will just tend to 1 over 3. So when you put in 2, you get -2. And as x gets really, really big, it will tend towards a third, okay? And it won't be able to exceed that. Now, if you're not quite understanding how we're talking about this with limits, what you could just do is on your calculator, you could just put in a really big value of x, okay? So put in like 1,000 or 10,000 or something, and you'll see that you get a number that's almost a third, okay? And as I explained earlier, it's because that -4 and that -5 in the function, they don't really add much to, it doesn't really change the function that much at that stage. It's the x's that are doing, it's going to be important there. So in terms of what my range is, so my range for g, my lower limit will be -2, and my upper limit will be positive a third, okay? Make sure you've got a less than inequality there for both of these, because actually we can't have x equals 2, so we can't have g of x equaling -2. We just need to have g slightly above that. And then x tends to infinity, so it will tend towards a third, but it will never actually equal a third. So that's why we've got less than there as well. In the final questions video, we are going to look at some parametric integration. So we've got a curve C here with the parametric equations defined as follows, and we've got this region R shown in the figure that's bounded by the x-axis and the y-axis and the curve. And we're first going to show how we could set up our parametric integration, and then we're simply going to just do that integration in the second part of A. So let's look how we set this up. Now, earlier in this video, I mentioned how we could perform parametric integration, and that's that we do y times dx by dt, and then we can integrate that with respect to t. So what we're going to need to do is to find dx by dt first. By the way, something I didn't mention at the start is you don't get that given in the formula book. Same with the differentiation as well. So really important that you learn that. So if x is 2 cos 2t, okay, well, we in our integral here need a dx by dt. So I'm going to need to find dx by dt. So we're going to differentiate 2 cos 2t with respect to t. So that's going to become -4 sine 2t. So that means that y dx by dt, so y is just 4 sine t, and dx by dt is -4 sine 2t. So we've got y times this dx by dt. And if I look at what I'm trying to show, now remember, this is always something to try to, have in the back of your mind with show that questions, is you are showing the steps how you get there, but obviously you can have a look ahead to the format it's supposed to be in. Now, if I'm looking at this format it's in here, I can see that, well, we don't have any angles that are 2t. We've just got sine squared t and cos t. So that would make me think that, I need to deal with the sine 2t. And what I can do is use the fact that sine 2t is 2 cos t sine t, okay? Using my double angle formulae. So that's going to be -8 sine t cos t. Okay, sine 2t is 2 sine t cos t. So I'm just then timesing that 2 sine t cos t by that minus 4. So what I have is 4 times minus 8 is minus 32. Sine t times sine t is sine squared t. And then I've got the cos t there as well. Now I know what you might be thinking. I've got a positive 32t in what I'm trying to show, whereas my answer at the moment has a minus 32. Don't panic. We're gonna look at how, why that is, and it's all to do with the limits. So what I also need to do is, when I'm looking at the integration for this, I need to make sure these limits are in terms of t. So what I'm going to sub in here. So I've highlighted here. I'm going between this value of x here that I've highlighted in yellow and then x is 0 as the lower limit. So at this point here where I've highlighted, I'm going to need to find what the t coordinate is going to be. Now I don't actually know what x is here, but I do know that y will be 0. Okay, and I know that at this point the x and the y will share the same value of t. So what I'm going to do is I'm going to say, well, 4 sine t equals 0. So therefore, if I solve that, t will be 0. So at this point here, t is 0. And now what we'll do is we'll find our other value here. So we've got our line of x equaling 0 that is bound between there. So what we're going to do is we're going to just sub in x equals 0. 2 cos 2t equals 0. So you end up with cos 2t equals 0. And you'd solve that to get t as pi over 4. So for this, not 4, t is pi over 4. So when we're looking at our lines, we've got x equals some constant, but we know that the t value there is going to be 0. And then for x equals 0, the t value is going to be pi over 4. So what actually this is going to look like is I would have 0 at the top, because that would be my the higher value of x has a t coordinate of 0. And then you'd have pi over 4 at the bottom here. So we'd end up with this. But what I can do is if I switch the limits, I just need to times the expression which I'm integrating by minus 1. And then, there you go, we've got what we were trying to show. Okay, so that is going to be r equals that there. So then what we're finally going to do for this part, the final part of part A, we're going to find by algebraic integration the exact value of the area R. So let's just get rid of some stuff here. So we're asked to integrate this, and you might be thinking, well, do I need to do this by parts? Is there a substitution to make? But what we can do is, and we do the practice, we'll see these types of problems time and time again, we could do this by recognition, because I know that when I differentiate sine, that's going to give me cos. So what you want to try is try and see what happens if you were to differentiate sine cubed. Now when you differentiate sine cubed, that's sine t in a bracket to the power of 3, well, you would multiply by the power of that bracket. Okay, you can just use the chain rule to prove this. And then you'd multiply by the derivative of sine t. So if you did it by the chain rule, you'd let u equal sine t. So differentiate sine t, you get cos. And then your u cubed would become 3u squared. Okay, that's why we've got the 3 there. So that sine cubed goes down to sine squared. So if we were to differentiate sine cubed, I would get 3 cos sine squared. That's almost what I want to have there. So actually, if I were to differentiate 32 over 3 sine cubed t, then I would get 32 cos t sine squared t as required. So what that means is, if I integrate 32 cos t sine squared t, it must give me 32 over 3 sine cubed t. So my answer here for the integration is just going to be that. So yes, you can do it other ways. You can do some substitution. You can, do other ways. But try and get in the habit of, if you see sine squared times cos, or if you see sine or cos to any power, and then there's just a single sine or cos next to it, try a higher power of sine or cos just by doing differentiation, and you'll find that actually that's really quick to do it that way. And yeah, again, the more you practice, the more you'll just see that. So now what we can do is we just simply plug in our limits. So we're going to sub in the pi over 4 and the 0. Now when I sub in pi over 4, so do sine of pi over 4, we're going to get root 2 over 2, but then I'm going to cube that. And then I take away the result of putting in the 0. Now sine 0 is just 0, so we don't need to worry about that. So calculating that, we end up getting 8 root 2 over 3. On to part B. I'm going to show that all points on C satisfy y equals the square root of ax plus b, where a and b are constants to be found. Basically, we're going to find the Cartesian equation of the curve. Now, in this case, we can't do what we did in the second question, which was we just made t the subject and subbed that in. What we want to do with ones where we've got the trig functions here is we want to just use our trig identities. So with my x and y here, I've got a cos 2t and I've got a sine t. So I want a trig identity that links cos 2t and sine t together. So I don't want to use sine squared t plus cos squared t equals 1, because they just rely on both angles being t. I need the one with the cos to have a 2t in there. So yeah, again, we're going to go back to the double angle formulae, and I'm going to use that cos 2t is 1 minus 2 sine squared t. Because what I can do with that is looking at the fact that, well, x equals 2 cos 2t, well, that will mean that cos 2t is just x over 2. And if y is 4 sine t, well, sine t will be y over 4. And now I can just simply sub them in. Where I see cos 2t, I can replace that with x over 2. And sine squared t, well, sine is y over 4, so sine squared is going to be y over 4 squared. And then I can just start to simplify this as I go along here. So I've just got here a half x minus 1 equals minus 2 y squared over 16 here. And so minus 2 over 16 is going to be minus 1 over 8. So let's just simplify that. And because I'm trying to make y the subject, so I want to get y on its own. So I want to times both sides by minus 8 now. So when we do that, we'll get y squared equals 8 minus 4x. Okay, just timesing all the terms by minus 8, and I've just rearranged it about. And then I'm just going to simply square root this. Okay, so don't square root the terms individually. We're just going to square root there to get minus 4x plus 8. And in the final part of this question, we're asked to state the range of f. So we're just finding the range of this. Now, rather than consider this part, I would just go back to the start and say, well, y equals 4 sine t with a domain of 0 to pi over 2. And I know that the range of y as a function of t will be the range of my Cartesian equation. So what I can do is just sketch 4 sine t between 0 and pi over 2. So that would be sine t. If it's 4 sine t, the maximum value will be 4. Okay, sine t has a maximum value of 1, so 4 sine t will have a maximum value of 4. And if I sketch that between 0 and pi over 2, you're just sketching up to that maximum point there. So the range of y as a function of t is going to be 4, so that will mean that will be the range of the Cartesian curve. So the range of f is simply going to be, as you can see there, it goes as low as 0 and it goes as high as 4. Okay, so parametric equations there, they are tricky, but hopefully you've seen this video, you've got, there's also actually quite a lot of other skills we're bringing in. There's quite a lot of trig, as you can see, that comes into this. A lot of differentiation, a lot of integration as well comes into this. So it's a really good one to practice because it practices lots of other skills as well. I'm hoping just before the exam I can get in a binomial expansion video as well. We'll see how we go. But yeah, any questions, leave in the comments below. Happy maths, everyone.